Well, a warm welcome to everyone. Thank you for being here. Go ahead and get yourself ready with a notebook, grab a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, you might already notice it, the topic is piecewise functions. Piecewise functions are going to be a very important thing to understand when it comes to calculus, even pre-calculus. Now, what is a piecewise function? Of course, this is a function. And it's broken into pieces, which the name kind of suggests, right? Piecewise function. So what that means is instead of having one equation like f of x equals 3x squared minus x plus 2, where you could simply plug in any x value that doesn't violate the domain restrictions of the function. You can plug in any x value, calculate what f of x would be, and that gives you your y value. However, in piecewise functions, we're only going to take a piece and combine it perhaps with one or more other functions, but just pieces of those functions. So this is a great opportunity for us to turn our attention to the concept of domain. And we're going to take a look at our first example here so you can see more or less how this works. So in our first example, we have a function f of x, but as you can see, there are these two separate expressions. They're both on the left of a comma. This is telling us sort of the equation, how we would normally think of it. So these are how we're going to find our y values. These are basically our pieces, and these are going to allow us to find our y values. But they will not both exist at the same time, so we're going to turn our attention to the domain section of the piecewise function, which is right here. This domain tells us where a given piece is valid. So it basically tells us which x values we're allowed to plug in for that particular piece. As you can see, this top piece, I'll get rid of these circles. As you can see, this top piece, 4x plus 3, you can find y values by just plugging x into 4x plus 3. But we are restricted by this domain that we're only allowed to plug in x values which are less than or equal to 0. Well, what if we want to plug in a number that's greater than 0? As you can see on the row below, the domain for this bottom piece is all x values greater than 0. So if we want to plug in anything greater than 0 to the function, we will have to be using the bottom piece to calculate the y value. Okay, and I'll have a separate video on the graphs. I encourage you to try the graphs and try to graph these functions. If you'd like, you can first just graph both of these equations on the same grid. You'll see that there's some overlap, and then if you simply erase some of the overlap, you'll get the graph of the piecewise function. So I'll show you that in another video. But for now, I'd like you to practice evaluating a piecewise function. So let's do a little bit of practice. I'll first have you take a look at f of negative 2. I want you to evaluate this function f of x when x equals negative 2. So in order to do that, I have to identify which piece this input belongs to. The negative 2 belongs to this group, x is less than or equal to 0, because negative 2 is less than or equal to 0. So in order to evaluate this, I'm going to plug the x value, the negative 2, into the corresponding piece. Notice how I'm using this structure for x plus 3 because it goes along with any x values which are less than or equal to 0. And that means that I have negative 8 plus 3 or negative 5. So if I were graphing this piecewise function, the graph would contain the point negative 2, comma negative 5. Okay, great. Now let's try f of 0. What happens when x is equal to 0? Well, if we look carefully at the domain restrictions, this says x can be less than or equal to 0, meaning we're still going to use this top piece if x is equal to 0. So this would be 4 parentheses 0 plus 3. See, I'm just using this piece, 4x plus 3, plugging it in just like you would with a normal function. Really, the only trick here is you have to determine which piece you're going to be using. And once you determine which piece you're going to use, it becomes very simple. Very, very simple indeed. So let's do one last one with this example. Let's see, what is f of 2? Now, if we look at the input x equals 2, it now matches with the bottom domain. X is greater than 0 because 2 is, of course, greater than 0. So we're going to be using the bottom piece this time. This structure, negative x plus 1, plugging in the value for x as 2. So here we have negative x, but we're not going to use x. We're going to use the 2 plus 1. Of course, that gives us negative 2 plus 1, or just negative 1. Okay, great. That is the first example. Now let's move on to a slightly different example. We used two linear functions there. That was fairly straightforward, and the graph would just be consisting of two lines that seem to be kind of split. If we look at the next example, we have a new function, g of x. And again, you want to pay close attention to these domains. Sometimes, if they try to be kind of tricky, they might skip some values. So you need to be sure that these two pieces are covering all values of x. What do I mean by that? Well, anything that's less than 0 is going to be covered by the first piece. And then every other value for x, so everything that's greater than 0 or even equals to 0, is going to use this second piece. So it covers the entire span of x, so long as we're not plugging in any numbers that would, cause undefined. Fortunately, these pieces that we have here are always defined. There are no x values that would sort of ruin or break the math. We're not dividing by 0. We're not trying to take a square root of any negatives. Just very straightforward. So again, we'll have the opportunity to practice evaluating. G of negative 2, you want to pay close attention to that x value input so that you can figure out where we're going to put it. Which piece are we going to put it in? We're going to put that into the first piece. These domain restrictions are almost like there's like the adult version and the kid version, or however you want to think about it, the student and the parent, that kind of a thing. If we have someone that's like, I think of it like roller coaster rides, honestly. If we have someone that is less than 0, let's say they're under a certain height requirement, we're going to have to put them on this roller coaster. And they're going to enjoy that ride. Whereas if we have an x value, or maybe like someone is greater than or equal to a certain height, they're allowed to go on this ride. That's kind of how I think about it sometimes. So you want to make sure that you see what category does this qualify under. Negative 2 is less than 0, so we're going to be using this top piece, okay? After you've determined that, it really is incredibly straightforward to how you've been evaluating functions thus far. So we're just going to make sure we're plugging it into the correct piece. That's negative 2 squared minus 3, which is 4 minus 3 over 1. Okay, not too bad. And then let's try g of 0. I like picking values that are right on the cusp because it really makes you look carefully. Here's a 0. Does that mean we use the top piece? No, that says x is less than 0. This bottom piece says x is greater than or equals to 0, so we will be using the bottom piece. That gives us 4 times 0, pretty easy, minus 3, and that's just 0 minus 3, or negative 3. So negative 3, not too bad. It was right on the cusp between using the top function or the bottom function. But I think you can see now that it's very simple. Just got to check that input. So what would g of, 5 be? Well, since 5 is greater than 0, it qualifies to go into the second piece, the bottom piece. And then you simply replace it again like you were just evaluating a normal function. It's as if I just gave you 4x minus 3, told you to plug in 5, but really the thinking step here is figuring out which piece we're going to use. Because you could plug in 5 to this, that would be wrong. And that just gives us, 17? Yeah, the calculations are not intended to be difficult here. This is really more of a concept overview. Okay, I got a couple of more examples, and again, I encourage you to graph these piecewise functions if possible, or attempt to graph them. You should at least know what these individual expressions look like on a graph. Like this is just a linear equation, this is a quadratic, but it's not too bad. You should be able to handle that. Let's see. We have another function, h of x. This one's quite interesting because we have a line for part of it with a slope of 1, right? X plus 1. And then we just have this constant value. What does that even mean? Well, that means that if x is greater than 5, we don't really have to plug in the x. We just know that the y value will be 4. Remember that these portions are representing y values. So let's see how you do. Almost couldn't say that letter, h of negative 2, for example. Well, we gotta check. Negative 2 goes into which piece? It's definitely less than 5, so we're gonna have to plug that into the piece connected with the x less than or equal to 5. That's the x plus 1 piece. Remember that when we plug in our x values to a function, we're basically finding y values. Technically, we're finding h values, like values of the function, but if we were thinking about this on a graph, we would basically be plotting these h values as y values. Okay, so negative 1, no mystery there. And so if we plug in anything that is less than or equal to 5, if we plug in 3, if we plug in 4.9, even if we plug in 5, we will be using the exact same piece of function. So this would be 3 plus 1. And this would be 4.9 plus 1. And this would be 5 plus 1. But as soon as we go past 5, as soon as x is greater than 5, we will no longer be using that structure. So if we try to find h of 5.00001, which is just barely bigger than 5, but it is bigger than 5. We don't have to do any calculations. We know that it's just going to equal 4. Okay, so the graph of this is going to be most interesting to look at. I encourage you to take a look at that graph. All right, we'll finish up with this, which has a rational function and a little bit of a tricky domain to it. You'll notice that we don't have the inequalities here. So what exactly does this notation mean? What this means is that for all values of x except 2, use the top piece. Pretty simple. So that's what this x not equal to 2 means. You could break it up, but you really don't have to. I'll show you what it looks like just so that you can see a little bit more detail if I wanted to use inequalities. I could say it's 3 over x minus 2 whenever x is less than 2. It's negative 1 whenever x is equals 2. And then again, it's 3 over x minus 2 whenever x is greater than 2. But as you can see, that takes more time, takes more space, and it's really unnecessary. We can just indicate that everywhere except 2, this top piece is valid, okay? So we're going to take this and throw it out. Let's move it aside. There we go. Let's evaluate a couple of these. So let's take a look at k of negative 1. Because this is not a 2, it's very simple to figure out which piece it's going to use, right? In fact, if you look at the second piece, the bottom piece, that makes it really clear that we're only going to use that when x is exactly equal to 2. So k of -1, 3 over -1, right? You see what piece I'm using? I'm using the piece which goes along with any x value that is not equal to. So this would be 3 over -3, which is -1. And that's where you would have a point on the graph at y equals -1. Now what about k0? Some people might think this isn't going to work out because k0, well, it's a rational function. We can't divide by 0. But it's not a problem because there's not just an x on bottom. It's not just going to be 0 on bottom. We check to see if 0 is 2. 0 is definitely not 2. So it's going to qualify for the top piece, and let's plug that value in to the top piece. So 3 over 0 minus 2, which is -3/2. Very easy to do, right? Again, like I said, guys, once you know which piece to use, it just becomes basic evaluating a function. The graphing will be a little bit more interesting. In fact, this graph in particular is going to be maybe the slightly most different one out of all of the 4 examples, but I really want you to try to graph these. Do your best and maybe plug in some random function values or some random x values and see if you can figure out what's going on there. So if we try k of 2, that's right on the money for the second piece. X equals 2, so this is going to give us -1. And notice that we get a repeated y value. That's okay. Functions can repeat their y values. They just can't have 2 different y values that go with a single x value. So all of these x values were separate inputs. And this is how we evaluate piecewise functions. This is going to be pretty important when we look at early chapters in calculus, because calculus is going to have us consider what's happening on the left and the right side of certain locations. And so it's really crucial to understand how the function acts differently depending on what side of an x value we're at. We're also going to have to look at a concept called limits in the first chapter of calculus, and it's going to help a lot to understand piecewise functions. Not just algebraically, but also graphically. So in the next video on piecewise functions, I'm going to show you how to sketch all of these graphs. But in the meantime, I encourage you to try to sketch them, and then you can compare and tune in next time. I think that's enough blab out of me. If you liked the video, please like it, like on the actual platform, share, subscribe, all that good jazz, and keep improving your math. I'll see you next time in the video.